Okay, so we're going to talk about Stokes' theorem now. So, as I stated previously, Stokes' theorem is a higher dimensional generalization of Green's theorem, where instead of, with Green's theorem, we were subject to a domain that lived on the xy plane that was flat. Now, with Stokes' theorem, we are able to integrate over surfaces, and we're going to relate the surface integral to the integral along the boundary of the surface, which is going to be a line integral. Okay, and one thing that will be important with setting up Stokes' theorem correctly, just to make sure that you don't have a sign error, is that you need the direction of the normal vector to match up with the orientation along the boundary. And for me, what I find to be most intuitive is that that they need to satisfy the right-hand rule. So basically, if your thumb is pointing in the direction of the normal vector, and then your fingers will have to circulate or kind of twist in the direction that is depicted like this. Your fingers should twist in the direction that you orient the boundary. In this case, the boundary is the curve C here. The OpenStax book calls this positive orientation. So the idea that the direction of the normal vector induces an orientation on the boundary C to make it so that those two orientations match up, that means it's positive. Otherwise, if C was oriented the opposite way around, that would be negative orientation. I have a further illustration of this. So here in this picture, right, the normal vector is pointed this way, and so that induces the orientation going in this fashion on this top boundary. But then also, if you curve your way around, that induces the orientation going this way along the boundary C1. If instead of the normal vector pointing outward, if it was pointing inward, to make it so that the boundaries are oriented in the right fashion, you again have to satisfy right-hand rule. Right-hand rule then means that you go in this kind of clockwise fashion, which induces this orientation on this boundary, and will induce this orientation on this boundary. Okay. Perhaps it would make sense just to draw that. So this normal vector induces this orientation, which then passes on to like going this way for this boundary and that way for this boundary. If you can see that. Whereas with normal vectors pointed this way, that kind of induces that orientation, it's in the opposite direction, which then gives you that orientation and that orientation. Okay. All right. So now, what does Stokes' theorem say? So Stokes' theorem says that the line integral along the boundary is related to the double integral of the curl of the vector field. This surface integral, which is going to be it's a flux integral, because all the surface integrals are defined as flux integrals. But you're not talking about the flux integral of f, but of the vector field curl of f instead. And another way we can write this, which kind of is useful to notice for, I guess, later on, to set up kind of an analogy between these different theorems of vector calculus, is that C is actually the boundary of S, so you could write it in this way, and the circle is just emphasized that the boundary of S is going to be, they're going to be comprised of loops. You can have multiple loops, as in this example, but yeah, it'll be multiple closed curves, possibly multiple. I think in my examples it's only going to be like a single closed curve for each of them. So right, there's this remark that, so if the surface S is a flat region in the xy plane, then Stokes' theorem reduces to Green's theorem. The book kind of goes into how to see this, but it boils down to noticing that it boils down to noticing that this is equal to the double integral of the curl of f. Once you start to insert the parameterization, or well, I guess you kind of get halfway through inserting the parameterization, you have this normal vector, this unit normal vector, ds. So vector dot vector. So this ends up being yeah, so a surface integral like that. But this surface integral is now over a flat surface, and so then n ends up being equal to 0, 0, 1, which the book just says it's the it uses standard unit vectors, so it uses k hat. And once you take that and you dot it with the curl of f, if you think of f as the vector field given by p, q, and r, and you take the curl and you dot it, well, that dotting it with this vector is only going to isolate the k component of the curl, and so that is actually going to be that will be equal to py minus qx, which is exactly what Green's theorem says, that the circulation integral is going to be equal to this double integral of py minus qx. It's kind of bad that I wrote it here because this is not related to this first remark, but it's instead an elaboration of the second remark. So I don't know how I'm going to denote this, but yeah, it's yeah, something like that. Okay. Yeah, so that's just to expand on why this is true. Okay. What else? So one way you can think about curl is that it measures the extent to which the vector field f fails to be conservative. So you know that if the vector field f is conservative, then curl of the vector field is equal to 0. Right? That's because, like, as was previously mentioned, the curl of the gradient of a function is equal to 0. Right? And so if f is conservative, then that means it comes from a potential function. It means it is equal to the gradient of some potential function. So curl of grad of some function is always equal to 0. So we know this for sure. So consequence of Clairaut's theorem. So in this special circumstance, when the vector field f is conservative, Stokes' theorem actually simplifies to a fact that we already know about. Right? So if curl of f is 0, then plugging that into here, you would get that this double integral is equal to 0, which would then give you that this line integral over the boundary of a conservative vector field is 0, which is something that we already knew. Right? Conservative vector fields over closed paths, over loops, is 0, which is stated there. So it's just another way of checking that things make sense, making sure that all of the results are coherent. All right. Let's continue. So now let's see an example. Now this example just verifies or just checks that Stokes' theorem holds true in this singular example. So we have the example of this vector field given here and the surface S, which is a paraboloid, where z is greater than or equal to 0. So that just means that it starts up here and then it stops on the xy plane. It doesn't dip anywhere below. This paraboloid would continue on, but we chop it at z equals 0. We want the surface to be oriented outwards, which means that our normal vectors are pointed outwards. And you can see that that induces the orientation on the boundary, which is going in this direction. And then noticing our x and y coordinates, that is actually the standard orientation. So the xy coordinates are actually, if we sort of tilt our diagram, we'll end up getting that this is the orientation going in this way, which is the standard orientation in the xy plane. Okay, Right, so what we want to do is we want to verify Stokes' theorem, so we'll have to compute both sides of Stokes' theorem to do that verification. First, let's compute this side, the surface integral side. So we have to compute the curl of f. We have to then plug in the parameterization. So I've expanded out what this ends up being. Notice that here we are plugging the parameterization into a different vector field, not f, but curl of f. We plug in this parameterization r of u comma v, and then we'll have to compute this normal vector tu cross tv across the surface. Okay, so the parameterization we can easily get from the fact that this is a graph of a function, right? So we just have x, y, and then the expression for z being the function itself, the description of the function itself. So that is our parameterization of our surface. Then we compute the tangent vectors tx and t. Oh, that should be y. That should be y. Oops. Copy pasted. All right. So tx and ty. So that's a pretty quick calculation, just taking partial derivatives, and then we of course calculate the cross product of these two. So that should be a pretty straightforward computation at this point. X there, minus 2y, and then 1, yeah. So it's just calculating a quick determinant, right? So we have that, and then I'm doing one further verification that this is pointed in the correct direction. So the thing about computing this cross product, right, it depends on the arguments here. If you swap to these two, you'd get that the cross product would be pointed in the opposite direction. So then the normal vector would be pointed in the opposite direction. So in order to make things match up, we should just verify that this normal vector is pointed in the right direction, namely outwards. And by just quickly staring at this, you can see that it is. If we, like, say, plug in at 0, 0 at the origin, this would be 0, 0, 1, so it's pointed upwards. And so that's good. Also, we need to compute the curl. So that is comprised of setting the first row to ijk, the second row to the partial derivatives, and then the last row is the vector field that we're taking the curl of. So the vector field was y2z and x squared. So y2z and x squared. And then you go ahead and compute these. So this ends up being 0, that ends up being minus 2. So you get minus 2 there. For j, you have a minus in front, and then you have a 2x, and then 0. So you get a minus 2x. And then for the k, you have these two, which gives you 0, and this which gives you minus 1. There we go. Okay, so now that we computed all of those pieces, we can insert them into the formula for that we're trying to, or into the surface integral we're trying to compute. So we just computed all these parts. Tu cross tv is copied directly, I believe, although I guess I used x and y instead of u and v. Whoops. Okay, well. Okay, we can treat this as like in the abstract case, and then like this is just we've plugged in at x and y instead of u and v. So you get 2x and 2x, 2y, and 1. And now for this curl, so when we plug into this, we're plugging the parameterization r of x comma y into this function, into this vector function, basically. So when we insert that, well, okay, x becomes x, so that's pretty straightforward. So we do end up getting exactly this. Good. Next, we take this dot product. So I think that's pretty clear. Yeah, we do get this. And now I've also rewritten, I've spelled out what this double integral over d is. So thinking back to the diagram here, the domain D is this circle that is the projection of the surface onto the xy plane. So this flat circle is the domain D, and it's going to be a circle of radius 2, which is why we've parameterized it in this way. So let's see, maybe oh gosh, oh no, all right, that's jumped a lot. Okay, so D is 1, 2, 1, 2. So this is the domain D. Okay. And it's perfectly fine to do this in Cartesian coordinates rather than in polar. I wouldn't bother like converting this thing at all. So that's what I've opted to do. So you let x run from minus 2 to 2. You let y go from the function describing the upper half of the circle to the lower half of the circle. Or I guess I should reverse that. Lower half to upper half of the circle. Yeah, the dot product is fine. So now computing this inner integral, it's not too bad. You'll end up with this. Let's see if, I think there was something I needed to mention about this. So definitely these two double up when you have just a y, right? So integrating this will give you a y, which you then evaluate. That'll double up these two bounds because they're symmetric. The expressions are symmetric. They just have a negative there. So when you do the evaluation, you end up with two copies of this. With this one, when you integrate, you get y squared over 2, but then the y squared is going to square, when you evaluate, it's going to square these two functions. So then you end up subtracting the function from itself. That's why this ends up being 0 when you take the integral and you evaluate. The 1, when you integrate, becomes y, which again you evaluate, so that ends up doubling up. So that's why you end up with the 2 here. And then this cancellation has been there for a while. What's going on is that when we integrate over this x from minus 2 to 2, well, this is a symmetric domain on x. Notice that this is an odd function. Yeah, with respect to x. So what that means is that if I replace x by negative x, this part stays the same, but this part is going to flip in sign, which means that the whole function flips in sign. So that means that this is an odd function with respect to x, and since we're integrating over a symmetric domain, that's going to cancel out and give you 0. So ultimately, our integral simplifies down to this part, which I can then pull the minus 2 out, giving me this integral. And then this guy, if you just think about what it looks like geometrically, this is computing the area of the upper half of a circle of radius 2. It's, well, okay. I wonder if this thing recognizes semicircles. Maybe it doesn't. That's totally fine. But yeah, it's a semicircle. Right, as you should be quite familiar with, right? So instead of computing this through actually integrating, we just think of the area, right, below the curve. So it's 1/2 of formula for a circle of radius 2, which is pi r squared. So, then this simplifies out to minus 4 pi. Okay, so that was the first part. We computed one side of Stokes' theorem. Now we compute the other side of Stokes' theorem, which is the line integral. So we're going to need the line integral around the boundary of the surface. So recall that I can probably scroll up a little bit if my computer stopped jumping. Where's my cursor? Where is it? Yeah, so the boundary of the surface is going to be this circle of radius 2, oriented counterclockwise. So we parameterize it in a counterclockwise fashion, which is the standard fashion. So we just use cosine and sine, and then to set up the radius correctly, we just do 2 and 2. In the xy plane, so then z is 0. So this is a parameterization for the boundary of the circle. And so we just compute the line integral now. So this line integral of f dot dr, which we then plug into parameterization. Now the vector field f, what was that again? So f was y, 2z, and x squared. So y is going to be this function, right? So you can label this as x, y, and z. So when you insert it in, it matches up the f takes arguments x, y, and z. So these match up. So it's y. I think it was 2x, and then z squared. Is that no? I'm messing it up. Y, 2z, and x squared. Yeah, so y is there, 2z is there, and that's x squared. Okay. And then dot with r prime. So r prime is pretty straightforward. Just take the derivative of r, and didn't even bother doing that ahead of time. So we have that now. Okay, computing the dot product is also, so we have two zeros that cancel out easily, and we get this minus 4 sine squared of t. And we integrate that with respect to t. Now this integral should be pretty straightforward for you to handle. I would have to do it through like a reduction formula, just rewrite the sine squared as, I always get the order mixed up, but it has a cosine of 2t in it. So it's either 1/2 of 1 minus cosine 2t, or it's 1/2 of cosine of 2t minus 1? Or is it plus 1? One of them is a plus, I think. Yes, I always forget it, and I always have to like rederive it from double angle formula. But yeah, you know how to deal with that. Either way, this ends up being minus 4 pi. So we were able to verify that Stokes' theorem holds true for this example with this particular surface and this particular vector field. Okay. Right, so here's another example. This one kind of illustrates an instance when we would want to use Stokes' theorem. So we're asked to calculate this surface integral, curl of the vector field, and we're given this vector field, but the difficulty lies in the surface itself. So the surface is this crazy thing. So you don't want to parameterize the surface. Because I mean it's probably not possible to, not reasonably. So instead, by using Stokes' theorem, we can, instead of parameterizing the surface itself, we can parameterize the boundary, and we're told that we're told the orientation. Yes, so it says oriented outward, which means that I'm probably going to use a different color. What should I use? Maybe orange. No, maybe, I don't know if yellow is going to show up. Okay, so we want it to be oriented outward. I don't like it. Oriented outward. Okay, there we go. So yeah, apparently yellow does work. Oriented outward. And then what that's going to induce is it'll induce an orientation that goes, from our perspective, clockwise. Okay. So it ends up making I don't need to draw it as arrows. I can just draw it as little arrowheads like that. So it ends up being oriented clockwise from our perspective. Okay, and then you can also notice that if these tick marks are of unit length, then that means that this circle is a circle of radius 1. It is on the xz plane, though. Notice that. Okay, but okay, so there's a typo there. That should be a dr, f dot dr. Yeah, so Stokes' theorem says that we have this integral, so we can instead compute the line integral along this boundary curve C. So let's now parameterize the curve C. So because it's a clockwise rotation and it's also offset, notice that the center of this circle is not at the origin. It's instead at 0, 1, where this 1 is in the z coordinate. So you have to be a little bit careful thinking about this, and I think the PDF version of the book messes it up. The online book, I think, does correct it, but then the following calculation is a bit messed up. So I had to like fix it. I think I fixed it correctly. So the way to check that this works is we just need to like test it at 2 points. So first we'll think about it at t equals 0, and then at t equals pi over 2, because that's a 90-degree rotation. So at 0, it's going to be 0, 0, cosine of 0 is 1, so it's going to be 0, 0, 0. So we start out, if I can make it show up nicely, we start out at that red point, okay? And then we, okay, so maybe t equals 0, right, is going to be red. And then I'll make blue t equals pi over 2. Okay, I'll just complete this out. Okay, and at pi over 2, if we plug that in, we'll get the value 1 comma 0 comma, and then cosine at pi over 2 is 0, so it's 1. So you end up getting the point 1 comma 0 comma 1. So x is positive 1, z is positive 1. That lands you up here. Bit hard to see, but yeah. So that has given us the correct orientation for this. So the sine and minus cosine is giving you the counterclockwise orientation. The plus 1 is shifting the z coordinate up by 1. You can think of it that way also. Okay, so this is the parameterization. Now, to compute the line integral, right, so we insert the parameterization, so we go from 0 to 2 pi. We do f of r of t dot with r prime of t dt. F of r of t, what is f again? F is z 2xy and then x plus y. Okay, so z is this function, 2xy is this function, and then x plus y is this function. Okay, so that is f of r of t. And then r prime of t is the derivative of this, which is pretty easy to do. Next, we take the dot product of these. So then that's going to be, yep, this, and then plus cosine squared. And here I'm, just to make it easier for me to think about, what I did was I used one of the double angle formulas. So there's this identity, trig identity, that cosine of 2t is equal to cosine squared t minus sine squared t. One of the 3 ways of writing this double angle formula. So noticing that this is the negative of that, that's why I wrote minus cosine of 2t. And then, of course, both of these integrate to 0, right? Because they're sinusoidal. From 0 to 2 pi, it picks up a full period of cosine and 2 periods of cosine 2t. So of course the integral is 0. Or you could just integrate it and then evaluate it. You'll get sine of t and 1/2 sine of 2t. But yeah, it's gonna be 0. Okay. And now this remark. So yeah, notice that what Stokes' theorem is saying is that the surface integral only depends on the line integral around the boundary. So it's giving us this relationship, and so one way we can actually interpret that is if two surfaces S1 and S2 have the same boundaries C and the same orientation, then Stokes' theorem actually equates the two. Right? It equates them through the line integral along the boundary, which means that this complicated example with this this crazy surface can actually be simplified with a very simple surface whose boundary is this curve, namely the disk there. So instead of doing this double integral, or well, I guess instead of approaching it by doing the line integral, we could have instead done it as a double integral along the disk there, which I believe is what I've written here. So yeah, you can instead simplify the surface of the disk enclosed by the boundary curve C, and then integrating all that simplified surface. So yeah, that is another possibility. And here's a way that we can actually phrase this idea. It's that these flux integrals of curl vector fields, so notice like this is a curl vector field because it's curl of f and curl of f, right? These curl vector fields, when you take flux integrals of them, they end up being surface independent. So it doesn't matter what surface you're actually picking. So long as your vector field is a curl vector field, it's independent of the specific surface that you have. It only depends on the boundary curve and its orientation. You flip the orientation, it should introduce a negative. That's it. And this is really analogous to what happens with line integrals of gradient vector fields. Right? Vector fields that arise as the gradient of a potential function. We learned that they are independent of path. They only depend on the endpoints of your parameterization. And on the order as well, which is kind of where that flipping of sign can show up. If your starting and ending point are different, then that's actually analogous to flipping the orientation of the curve, right? If you started at this point and you went to that point versus if you flipped the orientation, that's going to introduce a negative into the evaluation. So there really is the kind of correspond analogy. There's really an analogy there. The flux integrals of curl vector fields are analogous to line integrals of gradient vector fields. Okay. Next, so this is another instance where you might want to invoke Stokes' theorem. So, say you're asked to calculate a line integral. The vector field f, that's fine, but the issue lies with the curve C. So the curve C is said to be the boundary of a parallelogram with these 4 vertices. Okay, so that's a bit bothersome. If you wanted to actually treat this as a line integral, you certainly could, but it's just going to be a bit tedious, because to treat this as a line integral, you'd actually have to parameterize all 4 sides of the parallelogram and then calculate 4 different line integrals over those 4 sides, and then you add all of those results together to get the final result, which would be the overall line integral over C. So it's doable, it's just tedious. So instead, if we use Stokes' theorem, we can kind of get around that complexity, so long as the region that we're integrating over isn't too bad. Usually when you invoke Stokes' theorem, there can be a bit of a trade-off, because what happens with it, if we actually, so I guess I should have mentioned this earlier, but okay, let's stare at it in this way. So actually, I don't like that, but let's stare at it from here, right? This more easily shows the trade-off. So over here, f can be more complicated, but the thing we're integrating over is simpler because it's the boundary. It's a one-dimensional thing. Over here, it's like we've effectively we've taken a bit of a derivative of f. So then the vector field we're integrating over is a bit simpler, but the region that we're integrating over can be more complicated. So in a sense, there's some trade-off when we're using Stokes' theorem, trading complexity in one place with complexity in another place. All right. Okay, but here, yeah, so our boundary is a bit complicated here. Instead, we'll is that the boundary complicated? Well, it's not exactly. Okay, so what I'm saying is a bit off, but it turns out that using Stokes' theorem here does simplify things. So first of all, let's figure out how we describe the surface. So instead of the boundary, we want to talk about the parallelogram itself. So let's call that guy S. And one thing that you have to notice, you have to kind of construct it, and maybe drawing a picture helps with this, but so let's say that we're working in the xy plane. So x here and y here. Z will be somewhere, but I'm not going to illustrate that right now. 2 here and then 2 comma. Oh no, that's wrong. It's 1 comma 2 and 0 comma 1 2. So if we project this parallelogram that's in three-dimensional space, if we project that down onto the xy plane, we end up getting this rectangle. Okay, and then what you can do is, knowing that this is supposed to be a parallelogram, it's supposed to be some flat object, although it's kind of tilted in three-dimensional space. What you can figure out is a function that will actually hit all of these z coordinates given these x and y coordinates. And so kind of by inspection or by playing around with it a little bit, you arrive at this. You'll arrive at this function that describes the parallelogram. So then that allows you to create the parameterization, because we're able to think of this as a graph of a function, so we just use this typical way of constructing the parameterization for the graph of a function, x, comma, y, comma, the function describing z in terms of x and y. And of course, we end up parameterizing that over this rectangle, which means that it's going to be it's going to have these bounds for x and y. In order to set up the integral for Stokes, it's going to be the double integral of the curl of f. And as part of the parameterization, we need to dot it with the normal vector, which is going to be t sub x cross t sub y, tangent vectors. Right? So we take the derivatives, which is pretty straightforward. We also then take the cross product, which I think is also a fairly quick computation. 1 there, yes, minus 1 there, and then, well, minus negative 1, so it becomes 1, and then here it's 1. So, yeah. Then for curl, well, we're doing curl of this function, vector field function. So, so you can set it up like that and go ahead and compute it. So I think because this was still part of this unit, let's talk through that. So expanding along, the cofactor for I is going to be, it's going to have z here and then minus 2z, which gives you a minus z. The cofactor for j is going to have this derivative, which is 0, and this derivative, which is also 0. Right? And then the cofactor for k is going to be these two, which is 2x, and this is which is going to be minus x. So you get 2x minus x, which gives you the x there. So that's the curl of f. Okay, now inserting that into the formula for Stokes' theorem. So this was what we wanted to compute. That was what the problem asked us to compute. By using Stokes' theorem, we say that that's equal to this guy. Inserting the parameterization, we give that. Notice also that by doing that, I've switched myself from S and ds, the surface, to d and dA, which are the flat, a flat version. So that's actually, this is in the xy plane. This is me integrating over this rectangle, which I'm actually calling d in this case. Okay. So yes, then we insert everything in. So let's see. First, let's check the bounds. So x goes from 0 to 2, y goes from 0 to 1. That matches up with the picture. Also, so our curl of f is minus zx. We're inserting the parameterization. So we insert this guy in. So x, y, and z. Minus z ends up negating everything here, which gives you minus 1 plus x plus y, which is whatever in there. And then 0 comma x, x is x, which is then going to be right there. Okay. Next we, okay, so t sub x cross t sub y I think is also just copied over, yeah. So then take the dot product of these two and then integrate that. So that should be straightforward. I think everyone can do that. Okay, I've also given some homework hints because these problems will take a little bit for you to figure out how to do them to some, well, they took me a little bit. Maybe that's because I'm rusty, but so hopefully these hints help out a little bit. At the very least, you can check that when you set up and compute the integral, you end up getting the correct thing. But I think the only integral that was actually a bit tricky to compute was this one. There's a bit more work just because there's a bit more terms. involved, but it's not difficult in terms of technique. It's just a bit larger of an integral. But then yeah, the main part about this is setting things up. So with this one, setting it up is took me a bit to figure out exactly what was going on. But yeah, basically you have to you're given C as the intersection of two surfaces, and you have to then like equate those two things and then complete the square in order to be able to set up a parameterization for that curve. Otherwise, it's not I wouldn't say it's obvious how to parameterize it without doing that. Once you can parameterize it, then you can set up the integral for Stokes to work. With this one, it was a little bit finicky to set up the integral correctly. I was missing something for like a bit of the time, and then I finally figured out what it was. So the main thing is that you need to. So you're told to integrate. You're told to compute a line integral over a triangle. So by using Stokes, you end up re-express that as computing a double integral over a triangle. I mean, setting up the double integral is fine, but the trick lies in getting the parameterization so that you get the normal vector correctly. If you don't, half the time I didn't have the normal vector correctly, and so then I wasn't getting the correct number. But once you have that normal vector inserted in, that converts your integral from a double integral over a surface to a double integral over the xy plane, and then everything works out nicely, and you can get this answer. This last one I think is straightforward, actually. It's not a big deal at all. So as long as you know how to parameterize an ellipse given the form of an ellipse, the implicit form of an ellipse, yeah, that's all it involves, really. So that should be pretty good. All right, that's it.